Good morning, everyone. This perhaps is going to be the chapter of this coming week, and I will work some exercise during class hours after exam this coming week, and I would like you to give some time to review these notes and the equations in the book, and perhaps look at some problems before coming to class on Monday. All right. So in chapter 11, so now we are pretty much going chapter 11. We are going to define unity of energy with respect to heat. The unit of energy is a letter Q, and is going to be used in this the remaining chapters. We are treating heat. So temperature is not energy. So energy is a quantity that is given by unity of joules, and this energy can be transferred from one place to another, and then to another. Like we study in mechanics, a falling ball that has potential energy that as it falls can be converted into kinetic energy. So the unity of energy is called heat, and so in this chapter we are reviewing that. We also introducing some constants specific of materials called specific heat, given by another letter C. So let's see what's going on in this chapter. So unities of heat. So we're gonna see it as given in calories. But see, this calorie is not the same as defined in food calorie, and I will try to explain that. What's the definition of calorie as a unity of energy? The calorie is the amount of energy required to increase the temperature of 1 gram of water, from 14.5 centigrades to 15.5 centigrades. So calorie is this unity of energy, and it's equivalent to 4.186 joules. So how much energy is required to take 1 gram of water, which is not a lot, and that is sitting at 14.5 Celsius, and raise its temperature to 1 centigrade, 15.5 Celsius. Well, you need 4.186 joules. Okay, so this joules, 4.186 joules, this unity tells you energy, which means how can you increase that temperature? You can shake the water, right? You can shake the water, put it in a container, and then you start shaking, and the energy that is being used by shaking this container, some of it might be transferred to the water, making it warmer. So heat is transferred to the water. Okay. You can also, in an easier way, to put it in the stove and then turn it on, and then you have heat being almost directly transferred to the water. Okay, so how does this calorie relates to food calorie? Well, 1 food calorie is in fact written in physics book with the capital C. So 1 food calorie, which is, let me see what it is, somewhere here. So 1 food calorie, the word is the same, except the one in chemistry or physics is written with the lowercase c, the food calorie is written with a capital C. So, in fact, one food calorie is equivalent to a thousand lowercase c calories. In other words, one food calorie is the equivalent of 4,186 joules. So if you think about energy, if you see problems that involves food calories, you have to convert that to calories of chemistry and physics. What is this? Okay, like this exercise. Look at this. We have a student that eats a bowl of cereal and milk and has 320 calories. Not very caloric, huh? So you go in the servings information, and then you read out 320 calories. So you have 320 food calories, capital C. This is equivalent, as we saw, 320 times 1,000 calories, lowercase, right? Because this is equivalent to 1,000 calories. So this amount of energy stored in a bowl of cereal is in fact 300 times 1,000. Now look at what I'm going to do. I'm going to take these calories and convert that to joules. 4.186 joules. So once you multiply all of that, I'm not going to do this, you're going to have certain amount of energy in joules. Okay? See how you're going to be doing this a lot. You're going to be converting calories into lowercase calories and then into joules. Okay? But let's see how this problem plays out. So you have a student, eats that many calories, and he wished to do exercise by curling barbells and say, okay, I ate that bowl, I want to lose the same amount of calories. How many flexions should he do? Curl should he do? See, here's the first thing you do. You convert that food calories into energy calories, physics calories. And then you say, hey, you know, every time you go up and down, you have mg8, the potential energy mg8. We studied that, remember? So, which means going up and down is 2 times mg8 times n, the number of curl you do, that gives that amount of energy. And then you find a number that might be, it's a very big number, over 6,000 times. I mean, all of this is very, I mean, we are doing approximations here, so you assume you are moving these weights with a constant speed, which we never do. There is a little bit of acceleration and deceleration, and in that, the work you ended up doing is, it might be even bigger than overcoming gravity, for that matter. So this is one thing you have to consider. The second thing is, when you do exercise also, your body change. You are pumping more blood through your system, and then you might, for that matter, you are burning calories, internal calories, as a result of that. Okay. Anyways, I will bring a chart this coming Monday specifying what type of organs and how many calories do they use just by being an organ in a human being. And you'll be amazing how the body burns calories even if you don't do anything. Okay. Definition of specific heat. So let's quantify the energy that is exchanged between objects. Like you have a cup of water and you put a little bit of ice in there. So energy is going to come out of the water, go to the ice, melts the ice, and then you have a final mix that might contain water and ice, or you might end up melting completely the ice, and then the final result is a liquid that has a certain temperature, less than it had before. So how can we account for that? How can we do all these quantifications and calculations? So this is the science of calorimetry. So the energy that is exchanged, the energy that is changed, the changing energy is equal to the mass of the object times a quantity C, that is the so-called specific heat, times the change in temperature that you are experiencing. See, this is the same thing as change in energy, which is equivalent to the final minus initial. If you could quantify an absolute value of energy, you can only, in heat, you can quantify only its change. And this is final temperature minus initial temperature. So the heat that is transferred to one object is equivalent to the negative of the heat the other object absorbs. Does that make sense? So when you study calorimetry, let's say, let me take this out. When you study calorimetries, and I hope to do some exercise in class on Monday, let's say you have water. The water is at a certain temperature, let's say 28 Celsius, kind of a hot water, because you left in the sun and is at that temperature, and you want to chill up a little bit. So what you do, you put a bunch of ice in there. So the water has a certain mass, and the ice has a certain mass too. Mice, right? Has a certain mass in kilograms. So calorimetry is the science by which you are going to figure what's going to be the resulting mixing of this system. Let's say, I'm not sure if this is true, but let's say that all your ice melts, and at the end you have only water, right? You have only water. So what is going to be the final temperature? What is going to be the final temperature? Assume you have your ice at, let's say, 0 Celsius. So you have initial conditions for your water, you have initial conditions for your ice. You know the final total mass, assume there is no evaporation, is going to be given by the sum of water and ice. So what's going to be the final temperature? Okay, so let's see how that play out. In a given example. Why it's taking some time. Alright, let's take a look at calorimetry. So, as I mentioned previously, the amount of heat that is absorbed by the cold material is equal to the negative of heat the hot material is sending out, or vice versa, if you want to play with negative numbers. But basically, this is the type of problems that you are going to be facing. You have a certain amount of something. Could be water, could be a metal, could be an aluminum, that is at a certain temperature and is placed in a cup that has this much of water at this temperature. So styrofoam means the cup is uninsulating. So you are not going to exchange energy with environment basically. And the system reaches an equilibrium temperature, and then you have some unknown, in this case the specific heat of that material. Okay, so then you play out your equations, mc del T plus mc del T, and del is always final minus initial, final minus initial. Okay, so when you add those two quantities, mass of water, specific heat of water, final temperature minus initial, plus mass of that you know, specific heat you don't know, final temperature of that material minus the initial, and then you have the problem solved. Okay, so in class I would take an extra hour just to focus on the problem. So I'm not going to be lecturing specifically on this subject, but I will be working on problems. Okay, hope see you then.